Olá, gente. Sejam bem-vindos. Hoje no seminário do Departamento de Raios Cósmicos, nós temos a honra e o prazer de ter o Jan Kaspar. This is how you pronounce, right? With sh.
Yeah, this is correct, but then the first name is Jan.
Jan Kaspar.
Yes.
So he studied particle physics at the Charles University in the Czech Republic. Einstein used to teach there, for those who don't know. He finished his PhD in 2011, and he works mainly on the TOTEM experiment, which is one of the smaller experiments at CERN. It sort of coordinates with CMS, of which our department is part. And he works on forward hadronic physics and also on detector calibration and reconstruction software. Like I said, I forgot to say I was going to introduce you in Portuguese. He will speak in English, but I also switch. Sometimes I switch languages. Ele vai falar da descoberta de uma partícula que é o Odderon, bastante famoso se você faz QCD, mas também não é sempre muito claramente definida, porque ainda é tópico de pesquisa o que é exatamente um Odderon. We still do not fully understand what an Odderon is on a conceptual level, but we discovered it. Vai ter perguntas depois do seminário. Se tem perguntas urgentes, claramente pode me escrever. If you have urgent questions, then please write to me and we can ask, but otherwise there will be a question and answer session after the seminar. And vai ter uma lista de presença, eu vou mandar link em alguns minutos. Jan, thank you very, very much. You can start.
Thanks to you for your invitation. It's a pleasure to present to you. So I will be talking about Odderon. I should say that I tried to prepare the presentation for kind of students, younger colleagues. So I deliberately decided to skip some details to make it somewhat easier. So, but if you have some questions, then please ask. I will try to do my best to answer that. So I go directly to the next slide. So on slide number 2, this is the plan of the talk. So the first question, which is kind of fair to ask, what is the Odderon? Because it's probably not a concept which is very well known through the field. So I will need to touch a bit of theory, phenomenology, and I will try to explain the language which we are using, because this might not be the typical one. Then in second part, which will be a very short one, I will try to outline let's say the typical experimental apparatus where we need to study these kind of phenomena and so on. And the third part will eventually be dedicated to how we convinced ourselves and hopefully also our colleagues that a state like Odderon, sorry, there's a typo here, exists really in the nature. Very good. So let me start with the first part. First, I would like to mention a concept of forward physics, and to be talking about something concrete, let me talk about forward physics at the LHC. So LHC, as you very well know, is an accelerator which most often is colliding protons with protons. And now you can imagine an event where at least one of the protons survives the collision and kind of continues almost forward. This is not a class of events which would be artificially invented, but about 1/3 of the LHC events is really like this. So there is good reason to study these events. When I said that the proton continues almost forward, this essentially means that the scattering angles are very small. We are talking about something like 10 or 100 of microradians. Last thing which I will come back to at some point is that the scattering energy, the square root of S, is very large. We are talking about something like 1 TeV. And then really to follow the most simple example in this presentation, I will focus mostly on the process of elastic scattering, which is a process where you have two protons in the initial state, they kind of bounce off each other, and you still have two protons in the final state. Then as the protons, they really scatter to small angles, it means that they exchange a very small amount of momentum, which is somewhat important for what I'm going to take later. The full momentum transfer square, we call it T. Most likely, you know, this is the typical Mandelstam variable to accompany S. Yes, and then here in this kind of Feynman-like diagram, you see this wiggle line, which represents the object which is mediating this process, and this mediator or exchange object has some interesting characteristics, and I can already say that the Odderon is one of those things, and this is the subject of the presentation. The next slide, yeah, you know, protons are strongly interacting particles, and we believe that the QCD is the theory of the strong interactions. So we could believe that we can really use the QCD to get predictions, but there's a catch. The catch is that in forward physics, quite general, in elastic scattering even more, there is no hard scale in the process. I was talking about small momentum transfer between the protons. So what happens that the QCD coupling is high. There's kind of an illustration of that. So this is the coupling strength as a function of the momentum scale in the process. And as I was saying, that we are kind of less than 1, so we will be kind of here somewhere there out of the picture. So it's really a region with high coupling, and that's why we are probing the non-perturbative regime of QCD. And as you know, this is kind of very difficult regime to handle computationally. So essentially, we have no first principle predictions from QCD. So of course, as the QCD is not easily applicable, people were thinking of an alternative, and I really put the alternative a bit in quotes, because people were not really thinking, or at least in the way what I'm going to say later, it's not an alternative in terms of dynamical structure, but it's merely looking for a language where some things might look easier and easier to understand. And one of the things of these alternatives is the Regeer theory. I don't wish to go into detail, so I just wish to sketch the basic essence. So as you probably know from theory courses, that the scattering amplitude can be represented in different terms as a function of momentum, impact parameter, or the angular momentum, like the partial amplitudes. And these are actually the partial amplitudes which are the basis or the starting point for the Regeer theory. So you can take the partial amplitudes AL of T, the L is the angular momentum, and you can try to think to generalize it into a function of the momentum L, where this could be actually a complex number, such that whenever the L would go to a real integer, it would reproduce the original partial amplitudes. And then under a series of kind of plausible assumptions, one can show that this interpolating function has singularities and in particular the poles whenever L equals some function of the T. And this function alpha of T, this is called Regeer trajectory. And then pushing even further, one can show that in the T channel, this scattering amplitude can be actually written as a kind of sum over the Regeer trajectories, which would contribute to that process. So this is this sum over this I, and then the amplitude RAY is proportional to the S to the power of alpha. So the interpretation is that you can identify what are the Regeer trajectories which contribute to the process, and each of them actually can be seen as an exchange of a Regeer trajectory or a region. And then what is actually nice about this is that if you would someone give you the list of the rigid trajectories which are supposed to consider, and you would be looking at high S. That's why in the beginning I was saying that at LHC we have really large S. Then you can only retain the contribution with highest alpha, because all the others would be superseded by this high power of S. So you see that only looking at the analytical structure, there are certain statements which are very strong and kind of leading to a simple picture which can be made. And up to now, we didn't employ any kind of dynamical model. It's just kind of looking at the problem from the right side, and you can already tell quite a lot. And this is why I think people really stick to this rigid theory language, because it's telling quite a lot. So the only remaining detail is to find what the rigid trajectories are. What are these functions alpha of t? And some comments of this are on the next slide. So this time, looking at the S channel of the interaction, one can show that the singularities or the rigid trajectories actually correspond to bound state and resonances, where the T can be identified with the square of the mass, and alpha of T is the spin. And then here you see this is the plot which people made at that time, really kind of taking the mesons they know, and they put it on the plot, and you see the spin versus the mass squared. And what they found, actually the trajectory, the alpha of t, seems to be linear. So this is the simplest case ever they could think of. And again, they thought, if this is so simple, that there must be at least a grain of truth on it. I mean, of course, it's not clear that what you see in this kinematical domain of this S channel can be extrapolated to the T channel, but actually it works quite well. The next thing which is kind of important for the next discussion is, if you look here, that the value of the alpha at t equals 0 is about 0.5. Why it is important is that from the optical theorem, which relates the total cross-section, that is the probability that anything would happen when the two protons meet, is proportional to the imaginary part of the scattering amplitude at t equals 0. And then from the Rajah theory, you can get the relation that the total cross-section is S to the power alpha minus 1. So if alpha is 0.5, then this exponent would be minus 0.5. That's why from the rigid trajectory, if you take only these trajectories here into consideration, the prediction would be that the total cross-section would decrease with energy. Up to the theory, now a bit of phenomenology. So here, this is a busy plot, but the only thing which I want to look at are the red points. The red points, they are showing the total cross-section as a function of the scattering energy. And then on the previous slide, I was saying that the prediction was that it was supposed to be decreasing. And indeed, if you look at the very low energies, it was decreasing, but somewhat as of something like 100 GeV, the cross-section was going up. So simply to reconcile the theory with the data, people said there must be something else than just the meson trajectories. There must be something new, and they called this rigid trajectory Pomeron. So this is a trajectory which must have the alpha at t equals 0 greater than 1. That's why the S to the power of alpha minus 1 would be an increasing function of the energy. And then second thing which I would like to show in this plot, if you look again at this low energy area, you see there are actually two curves which eventually merge into one. And these two curves, these are the measurements for proton-proton and proton-antiproton. So they are kind of split in the beginning, but for high energies, they are kind of compatible with one function. That's why when people first postulated the new Rajah trajectory, they said this would be so-called crossing even. Crossing even means that the amplitude which would contribute to the proton-proton and proton-antiproton scattering would have the same sign. But actually, if you do this, you can also already say, okay, and what about an Odderon? Odderon would be kind of crossing odd partner of the Pomeron. So this would be also a trajectory which has the alpha kind of 1 or bigger. But still, this would be an effect which is significantly weaker than the Pomeron. And most importantly, an Odderon would be a crossing odd object, which means the amplitude which would contribute to the proton-proton and proton-antiproton would have opposite signs. This means an Odderon is something which can lead to differences in proton-proton and proton-antiproton scattering. And this is something which I will come back later on, because this is an experimental feature which we can find in the data, and really proving there is a difference, we can go back to saying, yeah, there must be the Odderon, because this is kind of a smoking gun of this object. So up to now, I was trying to introduce what the Odderon is, somewhat how this happened historically, again, really skipping lots of details. But as a physicist, I'm not really satisfied, because I would like to know what that Odderon is. So for that, I have 2 more slides. So this is kind of trying to at least mimic an answer to that question. So in general, what should that be? What is the object which is exchanged between the protons? And quite generally, this is supposed to be an object which is color neutral. Why I'm saying this? Because maybe look first on this at the diagram. So suppose that the 2 protons would exchange a gluon. Gluons, as I said, they are in a regime where the coupling is big. So the gluons would like to kind of couple to other gluons and emit more gluons. So in this kind of colored exchange, what would happen? There would be lots of other gluon radiation, and this would go to some other particles. So you would never have in the final state just two protons. So simply by observing 2 protons and nothing else in the final state, we can tell that the object which is exchanged must be color neutral. Second observation is that probably that object would be gluon rich. So after all, the gluons are the carriers of the strong force. And another argument is we are looking at large S. We are looking at small t. So actually, the momentum fraction we probe in the proton here in this vertex or the other one is very small. And then if you look on the PDFs of the proton at the small x, these are the gluon PDFs which dominate. So the object with the exchange is probably really rich in gluons. And maybe now I will try to evoke back the picture when I was talking about the correspondence between a rigid trajectory and some real states, real particles. So up to now, let's say I built the picture that there is some rigid trajectory, and then this is supposed to be linked to objects which are kind of color neutral, gluon rich. So the good question could be, what would be the real particles or real states linked to that? And the answer would be kind of glue balls. So what is a glue ball? Glue ball would be really a state of matter which is purely consisting of gluons. I found somewhere this kind of artist representation of that could be, so what do you have on the left side? This would be the ordinary matter, where you have 3 valence quarks which are held together by these wiggly lines, which are the gluons. But the glue ball would be kind of this thing. There are no valence quarks. These are just the gluons which hold together just by themselves. So this was just a general introduction, what that should be kind of from first principles. And then on the next slide, number 10, few comments about few theories which actually come to the concept of Odderon or Pomeron, both of them. So the first one is the perturbative QCD. I mean, of course, here the danger is that you do your perturbative calculations and try to extrapolate to a non-perturbative regime or domain. So in principle, this program may fail. Nevertheless, I think it's interesting, at least for the kind of perturbative, non-perturbative transition region where these calculations may well hold. So that people actually, if they consider these kind of parallel diagrams where you have these vertical lines, and then you have the connections here. So I drew the diagrams with 2 and 3 and so on. There can be 4 and higher order terms, but you need at least 2. You need 2 to actually have the color neutral object, because if you have 1, you have nothing else to kind of compensate the color. And these ranks here, they sort of represent the way that the gluons, they really want to couple to the things. But here, what I'm trying to say that the couplings are only internal to this object which is exchanged. There are no couplings which go outside. So this necessity of gluons to couple, this is kind of realized internally to that object. And then what is a big difference between the left-hand side diagram and the right-hand side diagram is, if you have just 2 vertical lines, it can be shown by algebra that this can only make a contribution which is crossing even. That means that it would make the same sign contribution to proton-proton and proton-antiproton scattering. While if you have 3, then this can give also crossing odd contribution. So the first one, which is kind of lower order, this would be Pomeron. And then the high order, this could be the Odderon, which can somewhat answer the question why the Pomeron is kind of more important, because this is lower order effects. Then another theory which is kind of helpful in that respect is Delta's QCD. I am no way expert for that one, but maybe just a couple of words of what that is. So people try to discretize the space-time with a lattice. So they put the quarks in the nodes and the gluons on the links between that, and they perform a numerical calculation of what the QCD would be on this finite and discretized lattice, and then they try to shrink the lattice parameter, the distance between the nodes, and extrapolate to what would be the continuous limit. It's by far not evident, it's difficult, there are many approximations in that, but if you look on the spectrum, you really find that the gluons, they really form the glue ball. So there are states which are entirely and only made out of gluons, which is kind of reassuring. And the last thing, which is kind of modern, this is this ADS CFD correspondence. Again, no way I'm an expert on that, but it's kind of interesting because this is the conjecture by Juan Madacena about the duality between a field theory, which would be the QCD, and a kind of quantum gravity theory, which is on this entire de Sitter space. And the interesting property of this duality is that you have a link between a strongly and weakly coupled theory. So if you have QCD in the non-perturbative regime, which is the very strong and difficult to solve by perturbative means, you can make this duality and look on this on the other side where the theory is weakly coupled. So this is much easier to handle. And again, you get kind of evidence that there should be things like the Pomeron and the Odderon, which I tried to introduce before. Yeah, the last slide before I change the topic. So here what I'm showing is the differential cross-section of the elastic scattering. The elastic scattering is a very simple process. So there is just essentially one parameter for the dynamics, which is the T, the form momentum transfer squared. And what I'm showing is simply because it has kind of a typical shape, and I will make references to this. So I wanted to introduce And also what is kind of interesting that in different T regions, there might be different physics. So like me commented, going from left to right. So if one looks at the really very, very small T values, there might be an interference between the electromagnetic and strong interaction, because not only protons are interacting via the strong interaction, but they are also charged. So there is kind of Coulomb scattering happening also, and this is happening really at the very lowest T values. Then there is a part which is typically called the diffraction cone, and this is the non-perturbative regime. So we are talking about T values which are point something, so really very small momentum transfers. And this would be the region where to look for the Palmaron and maybe Odderon. They should be seen here. And then something happens, and there is a typical structure of a dip and a bump, which fairly much looks like kind of an interference pattern. So one can really think that there is some interference happening. And then if you look at the very high T, then there is probably some transition to perturbative physics then. Good. Some comments about the typical experimental apparatus. So we are talking about protons which get to very small angles. This means they essentially stay in the beam and they stay in the beam pipe. So we need dedicated apparatus to see these protons. And I will describe it on an example of the TOTEM experiment. And the idea is essentially to turn the accelerator, the LHC, into a magnetic spectrometer. So what one does, that between the interaction point, this IP, and the detectors, which are called RPs, Roman pods, I will come to that on the next slide. You see there are many magnets. This Q, this means quadrupole, and D, this is dipole. So you can use all these magnets to kind of deflect the protons with a small scattering angle out of the beam, and then here at the detector location where you can put tracking detectors by the position of the Roman the proton, we can go back to the IP and determine what was the scattering angle and so on. Here there are a few pictures. So I said that we call these detector Roman pods because it has actually the shape of a pod, and Roman because the first group which invented this device was from Rome. That's why we call them Roman pod. So here you see there is a bellow, so all this part can move up and down, and this is necessary because we can only insert the detectors inside the beam pipe once the beam is stable. Before that, we need to retract them into safe position to avoid there are any troubles. This is a picture from the tunnel. So you see that there's one pipe, the other pipe. That one, this is bringing the protons to the interaction. The other one, this is the beam pipe with the outgoing protons. And here you see there is one Roman pod which is moving horizontally, another pod which is moving vertically, and so on. Inside the pods, we have a stack of silicon detectors, which are then shown in detail here. These are strip detectors, and they are always mounted back to back. So there is one which has the strip direction in this way, and there is a strip on the other one which is perpendicular. That's why we can reconstruct both coordinates. And then there is this edge which is facing the beam, and this is kind of special because there is very little insensitive margin, because we really want to go as close to the beam as possible in order to avoid there is a kind of dead space. Yeah, here I just wanted to say that there are many difficulties on the theoretical side for the elastic scattering, but on the side of the, let's say, the experimental signature, this is much easier. As we talk about an elastic scattering, we have two protons which emerge from the same vertex and with opposite directions. So you can look really for the signature. And here I just put some correlation plots. For example, here between the angles, and you see this is the angle which is measured in the left arm of the spectrometer, in the right arm of the spectrometer, and then you have in hand really a lot of correlations which you can employ, and that's why you're really sure that what you measure is the elastic scattering. So this was a kind of still introduction. So now I will start discussing the two different pieces of evidence that we have for the existence of the Odderon. And the first one, the first evidence, this is coming from the comparison of the proton-proton to the proton-antiproton measurements, which I said this is what makes an Odderon really this difference. So the program for this is really to compare the cross sections from proton-proton and proton-antiproton collisions. And where should we be looking at? As I said, we have at least two regions or two objects which might contribute to high energy differential cross-section, which is the Pomeron, which is the dominant one, and the Odderon. We want to look for that one, which is probably a small contribution. So we need to be looking at a place where the Pomeron amplitude is somewhat suppressed. And we also need to be looking in a region where the Odderon amplitude is not alone, because we need an interference or that amplitude with something else to make actually the different sign of the other amplitude visible in the cross-section. If the Odderon was the same, if you take the amplitude which might have a different sign, but you put the absolute square when you go from amplitude to the cross-section, this difference would disappear. And from that point of view, this dip bump region, this interference region, I was trying to show you before. And then there's actually a sequence of if-then statements, because if we observe the difference in the differential cross-section, it's saying that there must be a difference in the amplitude level. If there is a difference in the amplitude level, then there must be some crossing odd component in the amplitude. And then, which is kind of important, is only if there is nothing else that can be crossing odd contribution to the amplitude, then we can attribute that difference to the Odderon. I will come to this a bit later. So actually, this is something people have been thinking about for a long time, and they even tried to make a measurement. Here, what I'm showing this is the first one, which is coming from the CERN intersecting direct rings, which was probably the first collider ever. So this was done in the 1980s at the energy of 53 GeV. And there you see a comparison of proton-antiproton, which are the hollow dots, and proton-proton, which are the black dots. And then you see there is a difference. You also see that the error bars, they are not negligible. So the number of points where you can really have kind of big difference is small. Then there are a few points where actually they overlap with the error bar. So most likely the statistical significance of this observation would not be very huge. Then some people even had some doubts about the data and so on. But what I think is the biggest drawback of this kind of attempt is the energy, because at the small energies, maybe in the beginning, you remember I was saying we not only have the Pomeron and the Odderon, we have also the kind of normal mesonic regions, but their contribution dies off with energy. But at small energies like that one, you cannot exclude that other crossing odd regions might exist. And that's why if this difference is really true, you might be able to explain that one even without the Odderon. That's why most people were not really convinced about that, that argument. However, this is a great motivation or a great example of what can be done really at high energies. And this is probably the main point of this presentation, that this was written together by TOTEM at the LHC and D0 at Tevatron. So at Tevatron, they had the collisions of protons with antiprotons at the energy of 1.96 TeV. LHC is colliding protons with protons, and it can go as low as 0.9 TeV in energy. However, if you want to see the dip bump structure, and I try to motivate why we want to see that structure, then we need to be at the energy at least 2.7 or so. So the program is quite straightforward. We take the measurements by TOTEM, which were done at 4 energies, ranging from 2.76 up to 13 TeV. We would extrapolate these measurements to the energy where D0 made the measurements in P and type P, and we make the comparison. The important point here is that if we manage to do this, the theoretical interpretation is going to be much easier, because we are talking about TeV scale of the energies, where theoreticians really only expect that Pomeroy and Odderon would contribute to. So then if we manage to prove there is a difference, then we can be quite sure that this can be attributed to the Odderon. Some more details. So here I'm showing the measurements at the 4 energies by TOTEM, and you see they're kind of similar. So you always have this part which goes down, then dip, then the bump, and go down. You can also see some trends. So if you, for example, look at the dip, then with the energy, it always moves kind of to smaller values of T and higher values of d sigma over dt. So at the end, when we do the extrapolation, we have quite some trends to be checked. So we have some handles to make sure that the extrapolation is kind of reasonable. How this was done, that we identified 8 control or characteristic points through the shape of the distribution. So dip, bump, somewhere in the middle, and so on. So we had these 8 points, and we identified these 8 points at all the 4 energy measurements we had. And then we put them in a plot. So again, quite a busy plot, but this is just showing in different colors. You see, for example, the bump, the dip, and so on, the position in T, and the differential cross-section value at that point as a function of the energy. So then we have the 4 measurements by TOTEM. This is that one, that one, that one, and that one. And we want to extrapolate to the energy of the D0, which are the stars. So you can already see that the lever arm, which we have, is much longer than this small piece over which we need to extrapolate. Then in order to do the extrapolation, we made a fit. These are the fitting functions which we used. And of course, this is nothing which is carved in stone. So you can ask why we used those fits. And one of the answers is yes, because it's discarded data. And then what I find is kind of magic, that the same parametrization actually works fairly well for different points, which is by far not obvious, because maybe I scroll back. When I was describing this curve, I was saying that at different T's, this can be really different physics, which may evolve differently with the energy. But no, you see, I mean, all the lines are almost parallel, so, and they describe very well the data. So I think we managed to find something which probably has some at least small grain of truth inside. So at this moment, we could extrapolate these 8 control points to the energy of D0, which is shown on the next slide. These are the black crosses. These are the 8 points. But this is still kind of a discrete information. We need to have something smooth which interpolates for different T values, because we want to compare with the measurements of D0, where they made the measurements at their T values. So what we did, we had kind of T dependence, which we tested with all the measurements by TOTEM at the 4 energies. So presumably this is a parametrization which would also work for the extrapolation, and we made the fit. So this is kind of simple, and we also use that fit to propagate the uncertainty. So we made a series of Monte Carlo pseudo experiments where we know that these extrapolated points, they have uncertainty. So we kind of perturb their position up and down according to the uncertainty model and then repeated the fits. We discarded the fits which are unreasonable, and we were left with this color-coded unsettled event. So then we know what is the extrapolation from TOTEM, which is then compared to the 0 on this slide. There is an important detail which I'm not gonna discuss, that actually to get better significance, we also try to find a common normalization in different words to kind of factor out normalization uncertainties, which are not necessary for the comparison, as we are doing a relative comparison. Then you see the D0 measurements by for proton-antiproton. These are the blue points, which actually don't have any depth. That doesn't go down and up, compared to the proton-proton, which really goes down and goes up and goes down again. So I think qualitatively, this is quite easy to see there's a difference. Then what you can do, you can make, for example, the chi-square compatibility test, and you would find out there's a difference at the level of 3.4 sigma. Yeah, there's another detail that you need to determine the right number of degrees of freedom and so on. Okay, so from that point of view, we have a kind of hint there is something happening at 3.4 sigma. Then the last part, which is another piece of evidence for the existence of the Odderon from the so-called raw parameter. So you can ask, and this is a good question, what is the raw parameter? And the definition is here. So it's defined as the ratio of the real to the imaginary part of the elastic scattering amplitude at t equals 0. So the next good question could be, why raw parameter, as this looks as a quite synthetic definition? And the reason for that is again the theory prediction, which says that for Pomeron, the amplitude at t equals 0 is predominantly imaginary. Why from the Odderon this would be real? So I'm coming back to the fact that the Pomeron is much more important typically than the Odderon. So we are looking for quantities where we could see this smaller Odderon contribution. So if the Pomeron is typically imaginary, then the contribution to the real part would be small, and essentially most of what we see in the real part would be coming from the Odderon. So to put it short, rho is sensitive to the contributions from the Odderon. But then the problem comes, rho is essentially related to the phase, and and typically the phase would go out the moment you take the square and you go from the amplitude to the cross section. However, here I come to something which I've been neglecting almost through the talk, that the protons have electric charge. So there is also kind of electromagnetic or Coulomb scattering. So then when you calculate the cross section, you have the Coulomb part, you have the strong amplitude or nuclear amplitude, and they can interfere. So if you know this one from QED, for example, you can determine what is the phase of the other one. So this is the trick which we use to actually determine the raw parameter, and is the interference between electromagnetic and the nuclear one. As usual, there are details, so you can also imagine kind of Feynman diagrams with both QED and QCD exchanges. I will not go into that one. This is just a kind of visual representation of what I was saying before. So this is the differential cross-section as a function of t, and there are three contributions. The green one, this is only from electromagnetic or Coulomb. The blue one, this is only from strong interaction or the hadronic component, and the red one if you combine both. So you see this is kind of interpolating between these two. And then the next thing which you can see, there is a small gap between blue and red, and this is the interference I was talking about. So this small thing here, this is sensitive to the value of the rho, or this is sensitive to the phase of this hadronic amplitude. When of course you can say, yeah, this is a small effect. Would you ever have sensitivity to actually measure this? And for that, I have the next slide. So These two plots, they show the differential cross-section in a kind of relative coordinates with respect to some reference as a function of t. That the top one, this is a simulation for different values of rho. So you see there are kind of different levels or magnitudes of the interference, and you see what is the different distance between the curves. And on the bottom, these are the measurements. These are the black points. So you see the error bars are quite small. And then if you have quite a few points, so it's perfectly possible to distinguish between these curves. So we do have the sensitivity to do this measurement. And these are our results. They're put in a kind of word compilation of the data. So this is rho versus square root of s. And these are the measurements by TOTEM, these 2 points. Why we are putting these 2 points there is because this kind of represents the uncertainty because of using different fit techniques, different fit models, and so on. So we kind of bracket the truth between these 2 points. And you see these 2 points are distinctly different from the extrapolation from the smaller energies from this curve. So then you can calculate what is the level of incompatibility of our observation with respect to this prediction, and this is more than 4 sigmas. At this point, you can say, yes, so maybe TOTEM did a good measurement, but maybe this extrapolation is completely wrong. Maybe this model is wrong. We spent some time analyzing that, and some answer is on slide number 30. And actually, it's not our answer. It's answered by the COMPETE collaboration, who did quite a comprehensive study before actually LITU started, and they took into consideration a large number of models to describe total cross-section and the raw parameter for different reactions, proton-protons, also kaons, and so on. So they had quite some data. And out of these 256 models, when they were confronted with data, they retained 23 models being kind of good quality. And the prediction for the model from these 23 models are put into these plots. So the left-hand side plot, this is showing the total cross-section as a function of the energy, while the right-hand side plot, this is showing the raw as the function of the energy. And then what you can see in the plots that all the model predictions, they cluster in kind of 3 bands: the blue band, the magenta one, and the green band. And then in red, there are different measurements by TOTEM. And you see that when we talk about the total cross-section, only the red points, only the blue models are compatible with the data, while when we talk about raw, only the green models are compatible with the measurement. So there is no model whatsoever which would satisfy both the constraints from the signal TOT and the constraints from rho. I forgot to mention one very important thing. COMPETE had the models without Odderon. So this kind of excludes all the models which were considered by COMPETE. And still one could say, yeah, so COMPETE didn't take into consideration the right models, but there is something called dispersion relations. And this kind of says, when you take these relations without the Odderon, it says that the rho should be proportional to the rate of growth of sigma TOT with the energy, which is saying that whenever the sigma TOT would be growing fast, you would have the rho higher. So the trend, which is shown in these plots, and it's particularly shown for some models, it's more general. So there is no escape whenever you don't have an Odderon. So from that slide, I think we are able to show that no matter what you do, if you don't have an Odderon, you can't get compliant with the data. So the last thing which you may say, so now you have shown that without Odderon, you can't really reconcile data and the theory. And the last piece is, so do you have a model with an Odderon which can describe the data? And here there are just two models with some degrees of inclusion of the Odderon. And here you see, for example, if I take the blue one, the one by Nicolescu, that it goes quite well through the points of total cross-section, and then it goes quite well also through the points of the raw measurement. So the answer is yes, there are models which can describe the data, and these models do include the Odderon. Yeah, and this gets me to the summary. So I was talking a little bit about the theory, how the Pomeron and the Odderon concepts were created, that these are mediator objects which are exchanged in forward physics processes at high energies, and these concepts they actually emerge in different theories. They are a bit different things, but in sort of similar characteristics. I mentioned some of those. And then focusing particularly on the Odderon, this is an object which is crossing out, which means this can introduce difference between proton-proton and proton-antiproton. And then this was used as a signature in the experimental search. I try to motivate a little bit what that is. And for example, looking in the perturbative QCD, this would be a kind of a bound state, putting in really in quotes, of at least 3 gluons. As I was saying, if you have only 2 gluons, you cannot have the crossing out exchange. So you need at least 3 gluons. I tried to show with really few slides how the apparatus for detectors would look like for the forward physics, because it's quite different from other detectors, and that we have special detectors called Raman pulse, which are really inserted into the beam pipe to be very close to the beams. And at the end, I tried to show you 2 pieces of evidence that the Odderon does exist. One was by comparing proton-proton with proton-antiproton measurements, one by TOTEM, the other one by D0, and the other one, which was more technical, was by analyzing the raw parameter, which is measured by TOTEM. I would like to emphasize that actually both analyses were kind of model independent. We didn't look on very specific predictions or very specific models. We really focused on what makes the Odderon, like the difference between proton-proton and proton-antiproton. And we are kind of happy that whenever we try to get there with different approaches, we always get to the same results. So we are kind of confident that we can claim the discovery. Looking on the statistics, if we combine the significance from these 2 pieces of evidence, we get sufficiently above 5, no matter model we take. So I think we can really claim the discovery, which is in principle everything which I prepared. A small comment is on the last slide. So when I was preparing this presentation, this is mostly based on kind of these four resources. The first 2, these are kind of books or reviews, and the last 2, these are references to the papers about these 2 different pieces of evidence, the difference, and this is the raw one. And then I actually came across a very small write-up of a lecture, which, despite the name, it actually contains quite nice description of the theory, like the Raja theory and perturbative QCD, about the things which are used in the forward physics. And it's quite short. It has 13 pages. It contains references to other work. So I thought if there is a student who would be interested in looking at this would be kind of good further reading resource. And this is fairly much I prepared, so I can stop now. Thanks for listening.
Thank you very, very, very much. I mean, this is a sort of difficult specialized topic, and it was one of the clearest structures I've heard about this. Any questions? Emerson. I can.
Hi.
Yeah, go ahead.
Can you hear me? Okay.
Yes.
Well, first of all, thanks for the beautiful and detailed seminar, Jan. Second, the discovery of Odderon is very welcome news for the theoretical community. But I have a question regarding the value of the rho parameter announced by the TOTEM collaboration. I suppose you know some recent work showing that in principle, the rho value measured by TOTEM can be a little bit higher. For example, there is a paper from Ezela, Petrovi, and Tkachenko, for example. They are using the same nuclear amplitude used by TOTEM, but a modified formula for the Coulomb nuclear interference term. The value of rho is larger than the denoted by the TOTEM. So I would like to know your opinion about this reanalysis of the TOTEM data.
Yeah, thank you very much for the question. I particularly don't know about this reanalysis, but I have been in very close contact with Vladimir Petrov about his supposedly new formula. And I spend lots of time analyzing what he proposes, because as you said, this could have potentially a detrimental effect to our measurement. So I try to redo the calculations, and I actually made a publication a few months ago about this. So I read at the calculation really starting from the very beginning. So I use the Econla framework. I make all the calculations numerically to make sure that I don't make any mistake on the analytical level, and this purely numerical calculation could confirm the, let's say, analytical formula which we were using for the analysis. So my personal opinion is that I think we are kind of safe and sure that the formula which we use for the analysis is correct. Then if you like, I can point you to the paper which I wrote about that if you are interested. Yes,
I'm interested. But you know also the work from there is a paper from Giulia Pancheri, Srivastava, and Passetti. Do you know this paper?
No, this one I don't know.
Yeah, they use a modified version of the nuclear amplitude, and again the values of rho parameter is larger. I think the point of this Italian group is related with how can I say, if I remember, it's the observer that a zero in the real part of nuclear amplitude lies in the Coulomb nuclear region. So if I remember, the TOTEM has assumed a constant real part of the nuclear amplitude near to t equal to 0. And I think, if I remember, the Pancheri's paper treats this and says that it's not possible to consider a constant real part of nuclear amplitude because a theorem from André Martin, something like that. Do you know this work?
I do not know this work. I need to read it. I mean, in principle, yes, there is a theorem from André Martin saying that somewhere, and I underline this word, somewhere there should be the 0 in the real part, but it doesn't specify where. So it's not, as far as I know, it's not very, let's say, quantitative. Then we didn't use the assumption of constant real part. We used the assumption of constant rho. So this would be constant ratio between the real and the imaginary part. Then we didn't make specific. Actually, there were two publications which we did. So there was one at 13 TeV where we could get really precise results because we had lots of statistics. But then we also have an analysis at 8 TeV. And 8 TeV, we spend much more time. So there we probe different options. So we made fits with kind of constant rho assumption, and also what we call peripheral. So this would be a kind of different assumption on how the phase evolves with t. And surprise, actually, we didn't expect this. We got exactly the same value of rho. So yeah, if the situation is the same at 13 TeV, probably the choice of the phase dependence on T may not make huge difference. And there is one more point. The point is, here we are comparing the measurement at 13 TeV to previous measurements. So suppose that everything would now be reanalyzed with a different formula. Maybe everything would shift a little bit up or up and down, but what counts is the difference. What counts is the delta. You see, I mean, if you want to make the comparison and make a statement about compatibility or incompatibility, this is the delta. So even now, if you would use different formula and everything would shift consistently up and down, there would be no difference. So what is particularly important to us that we make a comparison with a method which was similar to the previous analyses. And then if you look in the literature, how this was done in the past, how people extracted rho, this was done with some methods. Here, I was saying that here, the lower point is most similar conditions to the UA4, for example, and so on. So although at 13 TeV, we didn't exploit all the different assumptions on this or on that, we at least have the one assumption which is quite close to what people did before, which is the constant rho assumption. And in that way, we hope that we are kind of consistent with the other points, and that's why we keep the right difference between the extrapolation and our measurement. So yeah, it's not a definite answer, but I think we have put in place several kind of protections that our kind of conclusion is the right one.
Yes, I understand. Thank you.
Thanks for your questions.
Further questions? I have two.
Yes, please go ahead.
Yeah, the sort of, just as a qualitatively, where does the dip and the hump, which seems to be pretty universal, what is the physical explanation for that?
This is $1 million question. So I can tell you that every model has a different explanation. So I think most, well, let me go to that slide. Most models I know of, and I don't pretend I know all of them, they kind of explain this as a kind of interference between different amplitudes. So there is a model which has one amplitude, which is describing that part. There is a model, an amplitude, which has this part. And then you get the bump, which is the interference between this component and that component, for example.
So like Pomeroy.
So yeah, this is kind of a Pomeroy, and this was an omega exchange. This was the model by Islam, for example. There are different models which have kind of, yeah, so far I was always drawing the diagrams where you exchange one thing, but if you really have this as to the alpha dependence, this can't go forever. You need some mechanism for unitarization. So you can have also a diagram which would be going like this, and then you exchange multiple things. So then you can have one amplitude, which is a single exchange. You have another amplitude, which is multiple, or it's kind of two, and so on. And again, you get interference. And then you probably have different models with different interpretations. So as far as I can tell, there is no consensus of what that is exactly supposed to be. Can you still hear me, actually?
Yes, I can. I can.
Good.
But there was an interruption for some seconds, but I think now is okay.
I see a message that Giorgio went to waiting room. Okay, Giorgio, can you hear us? Hello.
I think Giorgio had some problem.
Yeah, let's wait a little bit. Maybe he comes back.
Yes.
Hi, I'm very sorry. Something happened with my internet and it kicked me out.
But you're back.
Yeah, I'm back. I'm sorry about this.
Don't worry, no problem.
It's an issue of the 24. It's an issue of this period of giving seminars. All right, thanks. I guess it's destiny, the gods of electricity saying that this was. I will have one final question since you survived up until now. I mean, sort of in modern quantum field theory, a definition of a particle is a peak in the spectral function, which basically means that it's there at T channel, at S channel, and at U channel. You will see a peak. This is not the way of thinking about the Odderon, right? Since it only appears at T, there is no way to look for it in the S channel or in the U channel.
I mean, in principle, yes. I mean, if it exists in the T channel, it should also exist in the S channel. So there are experiments which are looking really at production. So, for example, you could have a proton. You could have a proton. There would be a yeah, you could have some particles. Now you can have a mixture of, for example, a pomeron. You could have a gamma, and I think you can create an Odderon, which would decay to something. So these are kind of experiments looking in general for glue balls. And then if you combine the quantum numbers correctly, you can really look for a glue ball which would have the quantum numbers of the Odderon. So this is also possible. It's kind of different thing, but what you say is perfectly right. Which I was trying also to say in the beginning. So the amplitude which you get, this is universal. This is in T channel, this is in S channel. So you get something in the T channel. In the S channel, you should really see the resonances or bound states, the peaks you were talking about. So yeah, this should be one thing which can be seen maybe a bit differently, but in different channels. So there are things being done.
Okay. Thank you very much.
I see there is also Graziano who has raised hand.
Oh, please.
Okay.
Yes, please go ahead.
Just a question. If we assume there are interferences between electromagnetic and nuclear interactions for low T, these interferences are interactions predictable or outside the theoretical model?
So there are theories which tell how to combine the Coulomb with the nuclear amplitude. The nuclear amplitude is an input to this calculation, because this is an object which we cannot predict from first principles. But suppose that someone gives you how this amplitude looks like, there are ways how to calculate that thing. So kind of the combined effect of the Coulomb interaction and the nuclear one. There are different approaches. One is really kind of take this kind of Feynman diagram and try to calculate the dominant contribution to this one. The other approach is based on the aconal framework, where you transform the Coulomb interaction to an aconal, the nuclear interaction into aconal, and then you say, I assume that the aconals are additive. You sum these aconals and you make the transformation back to the D space, and you get the full amplitude. Was this clear?
Okay, thank you. I understand.